Material and energy balance. This unit is almost all problem solving. There are only a couple of pages of theory. I want to walk through them with you. It'll probably seem pretty fuzzy or nebulous, but it will be better if you've heard it once than have not heard it. As you're doing the problems, you can recall, oh yeah, we talked about that. You can come back and look at this. It'll make more sense when you actually do the problems. So material balance or mass balance refers to processes used in industries to balance raw materials, processed materials, energy, waste streams, and products. The process is fundamentally based on the law of conservation of mass. And therefore this type of analysis is ultimately used to optimize production and minimize wastes. So you'll be solving equations. What equation will you solve? What goes in is what comes out. That's the equation. And that's true for steady state conditions, not for startup or shutdown. If you're starting up the process, you might be putting more in than what comes out because there's retention. Or if you're shutting down the process, you might be getting more out than you're putting in because you're emptying the process. But we'll typically work with steady state condition problems. The following generalization should be kept in mind in solving material balance problems, and this is what you really should hear. It is always safe to work in units of mass, grams, kilograms, pounds, tons. Mass is always conserved in chemical processes. Furthermore, when no chemical reactions occur, such as in mixing problems or separation problems like distillation, it's safe to work in moles. Moles in equals moles out. But in chemical reactions, the number of moles of substance may change. Check the coefficients of a balanced equation. For example, in the combustion of hydrogen with oxygen, we have 3 moles going in and 2 moles going out. So moles are not conserved. It is, however, safe to work in moles of atoms, since even in chemical reactions the number of moles of atoms will not change. There are 2 moles of oxygen atoms on both sides of this equation. When no chemical reactions occur, and this is for gases only, it is true that mole percent equals volume percent. What's that about? Recall the ideal gas law. It says that at standard temperature and pressure, the molar volume of any gas, and most gases are ideal, at STP is 22.41 liters. So if I have a mole of helium, it occupies 22.4 liters at STP. And a mole of oxygen, it occupies 22.4 liters at STP, irregardless of their masses. It's true because gases are mostly empty space. What does this mean? Well, if you combined 1 mole of helium and 1 mole of oxygen, there'd be 50 mole percent of each component in the mixture, but there would also be 50 volume percent since they occupy equal volume. So for gases only, mole percent equals volume percent when they're at the same temperature and pressure. Often we'll be dealing with air. It's used in many processes, so we need to talk about it. The percent composition of fresh air is 21% oxygen, 78% nitrogen, 1% argon. Now for many problems, most problems, it's sufficient to ignore the argon and just say it's 21% oxygen and 79% nitrogen, because nitrogen and argon are generally both inert in most processes. If we have 100 liters of air, we can say there's 21 liters of oxygen and 79 liters of nitrogen. We can say there's 21 volume percent, right? 21 of 100 volume percent of oxygen, 79 volume percent of nitrogen. Now, keeping in mind that a mole occupies 22.4 liters at STP, we could divide the number of liters by the molar volume, and we'll get these values. The moles of oxygen in 21 liters is 0.9369. The moles of nitrogen in 79 liters is 3.5246, and the total moles therefore is 4.4615. Now the mole fraction of each would be the individual number of moles divided by total moles, and notice the mole fraction 2179.1 is exactly the same as the volume fraction. The volume fraction would be 0.21, 0.79, and 1. So volume fraction, 21 out of 100, is the same as mole fraction for gases, provided they're at the same temperature and pressure. The molecular weight of air is useful when working in moles. So ignoring the argon content, using a basis of 1 mole of air, we can say that 79 volume percent nitrogen is the same as 79 mole percent nitrogen, and 21 volume percent oxygen is the same as 21 mole percent oxygen. That's the composition of air in volume percent and in mole percent. So let's go further. So 1 mole of air is 0.79 moles of nitrogen times the molar mass of nitrogen, 22.12 grams of nitrogen in a mole of air. 1 mole of air is 0.21 moles of oxygen times its molar mass is 6.72 grams of oxygen per mole of air. So if you add these two masses up, we find the molar mass of air is 28.84 grams per mole. Now the mass percent of nitrogen is going to be different than the volume percent or mole percent. The mass percent will be the grams of nitrogen divided by the grams of air times 100 is 76.7% by weight nitrogen. The mass percent of oxygen is the mass of oxygen divided by the mass of air in a mole times 100 is 23.3% by weight oxygen. Notice that these are different than the volume percents or mole percents, which are 79 and 21 respectively. One last thing here. It's often convenient to work in pound moles or kilogram moles instead of gram moles. For example, we know that the molecular weight of water is 18.015 grams per gram mole. We don't often say gram mole, that it's implied. But it's also true that we can say the molar mass of water is 18 kilograms per kilogram mole and 18 pounds per pound mole. Sounds pretty strange, but these are commonly used in engineering calculations. I have some rationale for that here, but I just want to summarize then the process for solving material balance problems, and then we'll get started. So step number 1 is draw a diagram for the process. Even a box diagram is just fine. Place all the available data in the diagram. See what compositions are known or can be immediately calculated, compositions, and see what masses are known or can be easily calculated for each stream. One of the given masses can be assumed as a basis, or you can choose a simple value like 1 or 100. So you can ratio all the other components to one component, or you can ratio them all to a convenient unit based on one of the components being 1 or 100. Equations can be written for the total material balance as well as component material balances. You may not know what that means, but I'll show you when we do the problems. If no direct solution can be made, algebraic solutions can be made. You'll need one independent equation for each unknown. Sounds like math class, right? Simultaneous equations can then be solved for unknowns. Recall, the sum of weight fractions is 1 in the same way that sum of all percentages is 100%. And equations can be written involving these. So that's it for the theory. We'll get started and do some examples. So please take a look at example 1 on page 6. Material balance example 1. So this has been kind of set up for you. 35,000 kilograms of whole milk containing 4% fat is to be separated in a 6-hour period into skim milk with 0.45% fat and cream with 45% fat. What are the flow rates in kilograms per hour of the two output streams from a continuous centrifuge which accomplishes the separation? The first step was to draw a diagram, and that's kind of been done. Here's the centrifuge in the middle. We have the whole milk
going in, and we have two products coming out. We have skim milk and we have cream. And then this person has put the various information into the boxes and worked out what they could. Now I'm going to walk you through the way I would approach this. The basic equation is that mass out equals mass in. You can write it the other way if you wish, but this just looks more familiar to me. What's the mass out? Well, we have cream coming out, and we have skim milk. Those are the two products, and the mass in was whole milk. We're asked to calculate the flow rate, kilograms per hour of cream produced and skim milk produced. We're told the flow rate of whole milk going in. Now I know in the problem I see x, y, and z, and those are good variables, but I like to choose variables that help me remember what I'm talking about, because I quickly forget which one is x and which one's y and which one is z, because they're all incognito. So how about if I call the kilograms per hour of cream, I'll make the variable c. So I'll say there's so many kilograms per hour of cream, plus the variable for skim milk, I'm going to call it S. There's so many kilograms per hour. That's an unknown. I'm trying to figure that out, actually, S. And that's equal to whole milk, which I will call W, or M if you wish. Now, the flow rate of whole milk is given. It's 35,000 kilograms per 6 hours. But we're asked to calculate it on a per hour basis, so divide that out and you find out that is 58.33 kilograms per 1 hour. So actually we have an equation. The right hand side is a value, we have it. We have two unknowns that we're trying to solve for, kilograms per hour of skim milk, kilograms per hour of cream. We have two unknowns, we need two equations. The equations will be mass out equals mass in, or mass flow rate out is mass flow rate in this case. So I'm going to say that's my first equation, and you can always write an equation like this, that is the total of all the components equals the total amount. Easy to do. Then you can write other equations for each component, if you recall that from the previous page. So we have a component fat, and then we have another component. Once you take the fat out, what's left? I'm just going to call it water. There's more than water, but I'll call it something. It's a water mixture. Now we are given the composition of fat in each of these streams. We're told that fat composition in the cream is 45%. So I don't know the flow rate of C, but I know whatever C is, 0.45 times that is the flow rate in kilograms per hour of fat that's in the cream stream. The fat in the skim milk, I don't know what the flow rate is, but I know it's 0.45% of the flow rate of the skim milk. So write these as decimals. 0.45% is 0.0045 as a decimal times the flow rate of skim milk. And that'll equal the total amount of fat. And we're told that in the whole milk it's 4%, so I can write that as a fraction. 0.04 is 4% times 58.33 kilograms per hour. You follow me here? I'm saying the total mass of cream plus the total mass of skim milk equals the total mass of whole milk. I can say for fat, 45% of the mass of cream is fat, and 0.45% of the mass of the skim milk is fat, and it's equal to 4% of the mass of the whole milk. We can also write an equation for water. Not that we need it, but for completion. If 45% of the cream is fat, then the other 55% of the cream must be water. Likewise, for the skim milk, if 0.45% of the skim milk is fat, then 99.55% must be water. So I'm going to say 0.9955 times the mass or flow rate of skim milk. That's the amount of water in that stream. And if the fraction of fat in the whole milk is 4%, then the fraction of water must be 96%, 0.96 times 5833 kilograms per hour. You can drop out the units if you wish. Okay, there are three simultaneous equations. We only need two. Let me rewrite it so it just looks more familiar perhaps. I'm saying let's solve these two equations. 1c plus 1s equals 5833. And I'll take the second equation, 0.45c plus 0.0045s is equal to, now I didn't get that value here, that's equal to 233.3 if you wish. That's 233. So if this were math class, you'd know what to do. You can substitute one in the other and solve for the values of S and C, and we'd have our values. And there's no problem with doing that by algebra, but there are a couple of ways you can do this with a little more expedience. Let me show you those. In your computer class, I showed you how to use your calculator to solve 2-variable and 3-variable linear equations. These are in fact linear equations, and your calculator does up to 3-variable linear equations, and we will relegate our problems to a maximum of 3 linear equations, so you can use your calculator to solve any of these. The example in the computer class notes shows you how in the calculator to solve for x and y in 2-variable linear equations. And just as a point of reminder, what are you actually doing? You're finding the point of intersection between two lines when you're doing this. The process for doing it is right here. It's in your computer class notes, which I will put on Blackboard. So you simply enter the coefficients as required in the equation, the coefficient of x, the coefficient of y, and then the constant, and it asks you for the next one, coefficient of x, coefficient of y, and the constant, and hit enter, and it gives you the solutions for x and y. So it's a really easy way to do it. Here it is for a 3-variable linear equation.
So let me show you how to solve this equation on the Sharp calculator. I'm using the ELW516XG. The process on the other Sharp calculators is very similar. The exact details for the various Sharp calculators are given in the notes on Blackboard for the computer class. To make this as simple as possible, let's enter a simple equation. We'll have 2x plus 3y equals 4, and 5x plus 6y equals 7. We'll be entering the numbers 2, 3, and 4, and 5, 6, and 7. So choose mode. We want the equation mode, which is number 4. Choose 0, which corresponds to a 2-variable linear equation. Enter the values. 2, enter. 3, enter. And 4, which is the constant, enter. Second equation, 5x plus 6y equals 7. And that's it. X is -1, y is 2, the determinant is -3. We don't need the determinant. So we're going to solve this problem using matrix operations in Excel. 35,000 kilograms of whole milk containing 4% fat is to be separated in a 6-hour period into skim milk with 0.45% fat and cream with 45% fat. What are the flow rates of the two output streams? So for 6 hours we have 35,000 kilograms. On a 1-hour basis we'll divide by 6, and that's 5833 kilograms per hour of whole milk that's being separated. A basic equation is that mass out equals mass in. So the mass out is the mass of the cream plus the mass of the skim milk, and together that must equal the mass of the whole milk that went into the system. we have two unknowns, the flow rate of cream and the flow rate of skim. We'll need at least two independent equations. So the first equation describes the total flow through the system. We can also write an equation for each component in the system. So for example, for the fat, we don't know how much fat is flowing in the cream, but we do know that whatever the flow rate of cream is, the fat is 45% of it. So I can say 0.45 times the flow rate of cream. Similarly, we don't know how much fat is in the skim milk, but it represents 0.0045 times the flow rate of skim milk. That's 0.45%. So write your percents as decimals. And that total amount of fat that's in the cream and the skim must equal the total amount of fat in the whole milk. We're told that's 4% of the whole milk by mass. So here I've written 5833 is the total mass of whole milk, and 4% of that will represent fat, and that number is 233. So I put that here. We can also write a third equation. We don't really need it, but let's do it for sake of completion. We can write a third equation describing the flow rate of the non-fat. Now I've just called it water. So of the cream stream, 55% of it is non-fat, plus the non-fat in the skim milk is 99.55%. That's 100 minus the 0.45%. So that's 0.9955 times S. And then the total mass of that will be equal to, we're given, it's be 96% of the total mass of whole milk. And that comes out to be 5,600. So these are the basic three equations that you can write. Now to solve it in Excel, you want to take the coefficients of the variables. So these are the coefficients of the variables of the first equation, 1, 1, and here's the constant. 0.45 and 0045 are the coefficients of the variables of the second equation, and here's the constant. Likewise for the third equation, coefficients of the variables and constant. So we're going to choose any two. I choose the first two, but any two will work. So to solve this in Excel, we have to multiply the inverse of the matrix of the coefficients of the variables times the matrix of the constants. So we need to get the inverse first. I'm going to take the first two equations, these two. I want the inverse of this matrix. So first select the cells where the inverse matrix will be displayed. Insert a function. The function is called M inverse, and say OK. Now Excel is asking what array do you want the inverse of, so simply select those 4 cells. Do not press OK. Anytime you're asking Excel to return multiple values, hold down the Control and Shift key, and while it's held down, press and release the Enter key, and you'll get the inverse of the matrix of the coefficients of the variables here. We want to multiply that by the matrix of the constants. So I'm going to put these two values right down here just so that we know what we're doing. Excel will return the variables themselves as a matrix. Select the cells where they will be returned. Insert a function. This is called mmult. That's multiply matrix. So I'm going to multiply array 1 by array 2. Now in algebra, the order of multiplication and division doesn't matter, but for multiplying matrices it does matter. It has to be the inverse matrix first, followed by the matrix of the constants. Once again, don't press OK. Hold down the Control Shift key and press Enter. And there's the solutions. Those are the correct flow rates of the cream and skim milk streams. Just as a check, the sum of these two should be 5833, so let's do that. Equals SUM tab and select what you want to add together, and there it is, 5833. So Excel makes solving linear equations very easy. Bear in mind that Excel will only solve square matrices, 2 rows by 2 columns, 3 rows by 3 columns, 4 rows by 4 columns, and so on.
So just to finish our problem, we determined that the flow rate of skim milk the variable S was 5368 kilograms per hour. And the flow rate of cream was 465 kilograms per hour. And as a check, you should add these because they should add to the total amount of whole milk, and that does work out to be 5833 kilograms per hour of whole milk. Here's material balance example 2 on page 7. Let's look at the diagram while we read it. In the flow diagram, we have a gas scrubber. So this is a gas scrubber. The idea of a gas scrubber is that a gas is sent through a stream of water, and the water will absorb particulate or absorb some gas from it, perhaps an acid gas or a contaminant. So water is circulated through the system. The water is sprayed through the scrubber. So what's here? Well, here we have inlet gas coming in, and it has no mass, and there's no water in it. Stream 1 is a recirculation liquid flow stream back to the scrubber and has a measured flow rate of 20 gallons per minute. Here's stream 1, 20 gallons per minute. It's recirculated through the scrubber and back. The liquid is withdrawn for treatment at stream 4, and this is 2 gallons per minute. So eventually we have to remove some of the contaminant from the liquid flow, so that's 2 gallons per minute is removed from the system. The inlet gas has zero moisture, stream 2, as we noticed. The outlet stream, stream 6, contains 10 pounds per minute. Pounds per minute, not gallons per minute. Calculate the flow rates of water in streams 3 and streams 5. So this is streams 5 is a makeup water. And how are we going to do that? Well, I guess we're going to make our basic equation that mass in equals mass out. First of all, I notice that most of my flow rates are in gallons per minute, gallons per minute, gallons per minute, gallons per minute. This is 0, so it doesn't matter. And I have one here that's in pounds per minute. So rather than convert everything to mass, I think I'll just convert this one from pounds to gallons. And we're given the conversion factor here. Let's say 10 pounds per minute times 1 gallon for every 8.34 pounds. So pounds cancel, and I'll have 1.20 gallons per minute. So all of my flows are now in gallons per minute. I can say the flow in is equal to the flow out, right? Well, the flow of what, though? I want to solve for x, and I solve for y. What you can do is consider one component of the process at a time if you wish. Let's try that. Let's balance the flow rates around the scrubber. So what's coming in and what's going out of the scrubber? So material balance around the scrubber. Well, I've got stream 1. Stream 1 is over here, 20 gallons per minute. And then I have stream 2, that's 0 gallons per minute. Those two are coming into the scrubber. Going out of the scrubber, I have stream 6, which is 1.2 gallons per minute. And I have stream 3, which is our only unknown. Let's try that. So we'll say stream 1, which is 20 gallons per minute, plus stream 2,
and that's 0 gallons per minute. Let's just check that. Okay. Stream 1 over here is 20, plus stream 2, that's what comes in. What goes out is stream 6 and stream 3. Okay, so that'll be equal to stream 6 plus stream 3. And stream 6 we determined was 1.2 gallons per minute. And stream 3 is what we're trying to solve for, that's y. So I'm going to drop out the units here, and I can say that y is equal to, well, 20 minus 1.2 will be 18.8 gallons per minute. So now I can add that to my system here. This is 18.8 gallons per minute. Now we're also asked to solve for x, so we could do a material balance around the circulation tank. So what comes in is what goes out. What's coming into the circulation tank? We got stream 5 coming in and stream 3 coming in. What's going out? Well, this stream, and how much is that? It looks like it'll be the sum of these two. It's the sum of stream 4 plus stream 1. Let's write that down. So I'm going to do material balance around the recirculation tank. Okay, I have stream 3 plus stream 5. That's what comes in. What goes out is stream 4 plus stream 1. Stream 3 we determined was 18.8 gallons per minute. Stream 5 is what we're trying to solve for, that's x. Stream 4 is 2 gallons per minute, and stream 1 is 20 gallons per minute. So x is equal to 22 minus 18.2. It turns out to be 3.2 gallons per minute. So notice how you can take each component in a system and calculate the material balance around that particular component and eventually get to where you want to be. Just another approach you could try. Let's do a material balance on the whole system. If you can, let's try it. So what goes in to the whole system must be what comes out if there's steady state, and I believe there is. So what's coming into the whole system in general? Well, streams coming in are stream 2 from the top and stream 5 over here. And what's coming out is stream 6 and stream 4. Anything else in the system is just circulating. So just my makeup and my depletions. So what's coming in? I'm going to say stream 2 was coming in and stream 5. I'll look at those again in a second. And what's going out is stream 4 and stream 6. So again, follow with me. Coming in, stream 2, but that's nothing, and stream 5. What's coming out? Stream 4 and stream 6. Anything else is just circulating within the system. Let's put the values in. Stream 2 is 0. Stream 5, well, that's what we're trying to solve for. That's x. Stream 4 was 2. Stream 6 is 1.2. X is equal to 3.2 gallons per minute. So mass in equals mass out. Flow rate in equals flow rate out. That's material balance.